So question 13 introduces bond enthalpies by sort of asking you a series of sort of conceptual questions to make sure that you've sort of understood what these numbers are all about before we get into crunching the numbers. So first of all, it just wants the definition for average bond enthalpy, which is the enthalpy change when 1 mole of bonds, in all these enthalpy definitions, remember it's always 1 mole. So when 1 mole of bonds of a particular kind are broken, and the important thing is that it's in the gas phase. And the point about it being average bond enthalpy is that it's averaged for a number of compounds. So that's the definition. The point about the gas phase is that if you were in a liquid or in a solid, when you broke one set of bonds, it would have an influence on the other bonds that were there. You know, so for example, if you had liquid water and you broke the OH bonds, that's going to affect the hydrogen bonding between the water molecules as well. So it becomes a complicated thing. In the gas phase, the molecules are all separate, and so it's much more meaningful to just talk about breaking a particular kind of bond in isolation, independently of other things. Nevertheless, the number is still going to be slightly different for different compounds. So if you compared, you know, a CH bond in methane, it's not going to be exactly the same number as if you measured it in ethene, for example. You know, those bonds will not have exactly the same strength, and so the bond enthalpy wouldn't be exactly the same, but they're quite close, and that's why it's still meaningful to calculate an average value. Obviously, if they were all over the place, the average would be a bit of a meaningless number, but generally they're quite closely clustered, and so the average is useful. So part B really just follows on directly from that and says, because we've calculated an average of a series of different numbers, the average won't exactly equal any of those individual numbers that went into its calculation. So if we use average bond enthalpies, it will only be an approximation to what the bond enthalpy is in a specific compound. Okay, so that's what we need to say, that the actual bond enthalpy in a specific compound won't exactly equal the average value. But as I say, the scatter is sufficiently small that calculations based on bond enthalpies are still useful and are actually quite widely used. Okay, so standard enthalpy change of formation of water, remember, is formation of 1 mole of water in its standard state under standard conditions from its elements. So that means that we have hydrogen gas plus a half a mole of O2 gas forming water, which, because standard conditions is 25 degrees C, is going to be a liquid. Okay, because remember, standard conditions 25 degrees C, 1 atmosphere pressure are the standard conditions. So having written the equation down, you can see what the problem is, because enthalpy changes when 1 mole of bonds are broken in the gas phase. And you can see the liquid water is not in the gas phase there. And therefore you can't use bond enthalpies to calculate that value, because it just doesn't relate to liquid water. You could use it to calculate delta H for that reaction if it was forming steam at a temperature above 100 degrees C, but not liquid water. If we did use bond enthalpies to calculate delta H for the formation of water, we would have this same reaction, H2, mole of H2 plus half a mole of O2 will give you a mole of steam. Okay, because that's all you can do is to calculate that. So we can calculate or estimate, remember it'll still only be an estimate because we're using average bond enthalpies, but we can estimate delta H using bond enthalpies for that. But we're interested in the standard enthalpy change of formation, which means that we've got to form liquid water. Okay, so this is the standard enthalpy change at 25 degrees C and 1 atmosphere, and so the difference is that. So what we've got to do is to think, well, we've got an extra step here. In order to get from there to here, we're going to get the value which we estimate from bond enthalpies, and then we're going to get this extra contribution. So this plus this will add up to that. It's Hess's law again, really, that we're using. So what do we think about this? Well, this is going from a gas to a liquid. So in that process, hydrogen bonds are formed, right? Because that's what holds the liquid water together. So the hydrogen bonds are formed, and as we know, whenever any kind of bonds are formed, that will be an exothermic change. In other words, delta H is negative. So whatever value we calculate for this, what we have to add on to it in order to get an estimate for the standard change is an exothermic change. And therefore the answer is that delta H of formation under standard conditions will be more exothermic which means more negative than the value estimated from bond enthalpies. Now, that's not, you shouldn't take that to mean that you can usefully do this, that you can calculate some kind of number using bond enthalpies and then make some sort of correction for it not being in the gas phase, because generally you don't have any idea what the size of that correction is. So really this is just to make the point that you mustn't use bond enthalpies unless everything is in the gas phase, because otherwise you're going to get the wrong numbers. Now, part E is a really important question about understanding the relationship between bond enthalpies and delta H for reactions. So I've just illustrated it with this sort of made up reaction here. So these are our reactants, AA and BB. So that means that we've got to break the AA bonds, and that would be 1 mole if we're going to calculate the enthalpy change per mole. So we're going to break 1 mole of AA bonds and the BB bonds, 1 mole. And you know that bond breaking is endothermic. Okay, whenever you break any kind of bonds, it's always endothermic. So in other words, that's a positive contribution to delta H for the overall reaction. Having broken those bonds, we can now make the new ones. So we're going to form AB bonds, and you can see we're going to make 2 moles of those. And we know that bond formation is always exothermic. In other words, makes a negative contribution to delta H of reaction. So the overall enthalpy change, which is that, is just the sum of these changes. So there's a positive change from breaking those bonds, and there's a negative change from forming these ones. And you can see the sign of delta H that you get overall therefore depends on the relative magnitude of these bonds, of these terms. If this positive term is outweighed by a bigger negative term, that means that the overall result will be negative. on the other hand, if this term is bigger in magnitude and outweighs the negative term, then your overall result will be positive. So the delta H of reaction can be either positive or negative, which is why you can have either endothermic or exothermic reactions. But you can see that what that relates to is how strong the bonds are. So if the AA and AB bonds, AA and BB bonds are weaker than 2 moles of AB bonds. Okay, in other words, if you have to put less energy in to break these ones than you get back out, it means that more energy is given out when the new bonds are formed than was taken in when the old bonds were broken. Okay, so if the old bonds are weaker than the new ones, you have to put less energy in to break the old ones than you get back out by forming the new ones. In other words, overall energy is given out so it's exothermic. Delta H is negative. On the other hand, if the bonds in the reactants are stronger than those in the product, so you have to put more energy in to break the old ones than you get out, you have a bigger positive term from breaking those than the negative term you get back from forming the new weaker ones, then in that case positive outweighs negative, so you get a positive overall result, which means you have to put energy in order to make the reaction happen. So that's then an endothermic reaction with a positive delta H. So that connection is really important, that you can see that whether a reaction is endothermic or exothermic relates directly to the relative strength of the bonds in the product and the reactants. And the simple sort of brief statement of that is that if the bonds in the products are stronger than those in the reactants, then more energy is given out forming those than is taken in breaking those, and therefore the reaction is exothermic. So question 14 invites us to calculate delta H for this reaction using these bond enthalpies. Remember, it will only be an estimate, but it's a reasonable thing to do because they're all in the gas phase, so bond enthalpies can be applied. Now, I would absolutely strongly urge you, when you get a problem like this, to draw out the displayed formulae of the compounds, because if you don't, it's very easy to miss some bonds out or count them twice or miscount them or whatever. And so although in simpler examples like this you might think, oh, I can easily keep track of them, it's just much safer. So that's going to be my starting point then, is I'm just going to write out that equation again, but this time with displayed formulae. So ethene is C2H4. Okay, so we've got that, plus water, and even water I'm going to write as a displayed formula because it helps me make sure I keep track of all the bonds. And that gives me ethanol, which is this. Okay, so every single bond shown, because that way I'm not going to miss any out when I come to adding things up. Now what I'm going to do then, and again I would always do this even if it doesn't tell you to, is to separately add up all the bonds on the left hand side and all the bonds on the right hand side and write down those subtotals before you do the calculation. because again, you're less likely to make mistakes that way, and if you do make a mistake, you're more likely to get credit for the bits you have got right. So what we'll do is just go through and say total bond energy on the left and on the right. Okay, so on the left hand side, let's just go through, and what we'll do is just tick off bonds as we've taken account of them. So we've got C double bond C, which is 610. And then you can see we've got 1, 2, 3, 4 CHs. Okay, so that's 410 times 4. And then we've got 1, 2 OHs. So that's 460 times 2. And then we can just do a double check and make sure that we haven't left any of them out, which we haven't. So that's going to be our grand total on the left hand side, which comes to 3,170 kilojoules per mole. And then we do the same on the right. So you can see this time we have a C single bond C, which is different, smaller bond enthalpy because you're only breaking one bond, not a double bond. So 345 for that one. And then you can see we have 1, 2, 3, 4, 5 CH bonds. So that's 410 times 5. And then we have a CO bond, which is 360. And we have an OH bond, which is 460. And then again, just do the check, make sure we haven't left anything out, which we haven't, and so we can look at what that lot adds up to, and it's 3215 kilojoules per mole. So that's the total amount of energy that we have to put in to break the old bonds, and therefore that's going to make a positive contribution to delta H. And this is the total energy we'll get back out from forming the new bonds, and so that's going to make a negative contribution. So what we can now do is write our calculation down, which is that the delta H of reaction is equal to plus this number because we're breaking those bonds, so it's endothermic. Sorry, I've written that number down wrong, make sure you don't do that, 3170. And a negative contribution for that one because we're forming those bonds, so that's an exothermic contribution, so minus 3215, which works out as minus 45 kilojoules per mole. Is our estimate of delta H for that reaction. Okay, question 15. We have first of all this equation, and we're asked to calculate delta H for that, again using bond enthalpies. So even though it's a relatively simple equation, I would again start by writing out the displayed formulae. So we've got two HH bonds and we've got an OO double bond, and then two waters is that. So again, take the approach that we get that the total bond enthalpy is going to be calculated on each side, so on the left and then on the right, and then we can find the difference to calculate delta H. So on the left we have, again, let's cross them off as we go along to make sure that we've taken account of everything. So we've got two HH bonds. Okay, so that's 436 times 2. And we've got one OO double bond, which is 496. So if we add that lot up, we get the total, which is 1368 kilojoules per mole. And then we do the same on the right, and you can see this one's easy. We have 1, 2, 3, 4 OH bonds, which is 460 times 4, which is 1,840 kilojoules per mole. And then you just have to remember to get it the right way around, and rather than just try and remember it as a rule, it's much better to think these bonds are being broken, and breaking bonds is endothermic. You have to put energy in to break bonds, so that the bond breaking number is going to be positive. So it's plus 1368. That's the endothermic breaking bond contribution. These bonds are being formed, so that's exothermic, so that's going to be a negative number. So minus 1840, which comes to minus 472 kilojoules per mole is the answer. Okay, so here's part B. Again, you can see everything is in the gas phase. That's really important for bond enthalpy things. You can only do it if everything's in the gas phase, because that's what the definition of bond enthalpy involves. So, same approach as before. Start with the displayed formula. So this compound is called hydrazine, and it looks like that, plus oxygen, and that gives us nitrogen, which remember is N triple bond N. So make sure you don't get these two types of nitrogen bonds confused. You could always do the dot and cross if you needed to make sure that you can see that that's got to be a single bond, that's got to be a triple bond, but you can work it out because you know nitrogen forms 3 bonds because it's in group 5, so that's the way it's going to be. And 2 waters, so we've got that and that. Okay, and then we can follow the same method, so we get the total bond enthalpies. On the left and on the right. So on the left we start off with our NN single bond, which is 160 kilojoules per mole. So quite a weak bond in contrast to the N triple bond N, which you see is phenomenally strong on the right hand side. And then we have 1, 2, 3, 4 NHs, which is 390 times 4. And then we have the OO double bond as well, which is 496. So putting all those numbers together, we get 2216 kilojoules per mole. And on this side, we've got N triple bond N, so that's 994. And we've got 1, 2, 3, 4 OHs, which is 460 times 4. And if we add that lot up, that comes to 2834 kilojoules per mole. So to complete the job, we then just need to do the subtraction again. So we get delta H of reaction is equal to, and again just remember that these are the bonds that are broken, and bond breaking is endothermic, so that's positive. If you just tell yourself that story, it's much safer than just trying to remember it as a rule that doesn't mean anything. So these bonds are broken, that's endothermic, so that number is positive, so it's plus 2216. These bonds are being formed, so that's exothermic, so that's a negative number, so minus 2834 is the sum, and if you compute that, that comes to minus 618 kilojoules per mole.